Hello everyone. Today let's solve the problem number 98. Validate binary search tree. Validate binary search tree. So what the question states here, we are given the root of the binary tree. See here, we are given the root of the binary tree. All we have to do is we have to determine whether if it is a valid binary search tree or not. If it is valid binary search tree or not. So here a BST must follow three rules, man. One is left subtree value should be less than or equal to the node values. So here node values means this one, whatever the node it consists of. This one here root, right? So the left subtree is this one and the right subtree is this one. Left subtree. I'll just write RST here. This is nothing but right subtree. This is RST and this is left subtree, right? So this one, let me make this one L, left subtree. So this is fine. So the left subtree value has to be less than less than uh, less than or equal to this one node value, and here it has to be greater than or yeah, less than or greater than this one. This value has to be right subtree value has to be greater than node values, right? So here this is fine. Two conditions, sorry, not the three conditions. This is the two condition basically. Here see, we have the value 2, the left subtree is having the value 1, which matches the criteria, and we have the value 3 here, which matches the criteria, means 3 is greater than 2, right? 3 is greater than 2. So this side left subtree has to be this one, the value has to be smaller one, smaller than the node value, and the right subtree value has to be smaller, greater than the node value, right? So I hope this part is completely clear. This rule we must apply recursively to all the nodes. This rule we have to recursively apply to all the nodes. So we will be going with the recursion. We will be going with the recursion for this particular problem, right? Just give me a second here. Mm, yeah. Um, so yeah, we'll be going with a recursion. So let's we are done with the question part. They have given us wonderful examples just for the sake of understanding. Same goes with the second example as well, man. See here, 5 1 4. So this we have here 1, and this one we are having 4. So this right subtree's value has to be greater than the node's value, right? So here it has to be greater than or equal to this one node value. Either it can start from 5 5 6 7 anything. It should not be less than 5, right? Accordingly with the criteria, accordingly with the condition that they have given. So this miserably fails. This cannot be this one binary search tree, right? Valid binary search tree. In that case we have to return false. We have to return false, right? So I hope this part is completely clear. Have they given another example? No, right? So this is fine. So they have given us wonderful examples just for the sake of understanding. Now let's move on with the approach part, right? As we are done with the question, as we are done with the question part and the examples that they have given, now let's move on with the approach part. First of all, I said that we'll be going with the recursion. We will be going with the pure recursion here, right? So just remember this one. We'll be going with the pure recursion, right? So the first step here is example, we have root equals 213. This one will be considering, man, 213, right? So we will start at root 2. We will start at root 2. This one I'm speaking of. We will be starting at root 2. We will be starting at the root 2. Left child is 1. Left child is 1. This one I'm speaking of. Left child is 1, which is less than 2. Which is less than 2. We have 1 which is less than 2. Left subtree I'm speaking of. So this satisfies the condition. This is good. This is good, right? So now let's consider the right. We have considered left subtree. Next, let's consider the right subtree. We have the value 3, and 3 is greater than 2. 3 is greater than 2. This also satisfy. This also satisfies the condition here. This also satisfies the condition. So will this is good as well. We'll be considering this one as good, right? So this is good as well. Right child is 3, which is greater than 2. This is good as well. So now we have to recursively check subtree that is rooted at 1. That is rooted at 1. So here we don't have the value for 1. We don't have value for 3 as well. So we have to check for 1 and 3. We have to check for 1 and 3. No children. No children for 1. No children for 3 as well. Right. So no children for 3 as well. All the nodes here until here, all the nodes, this part, all the nodes until here satisfy the binary search tree conditions, right? So that is the reason we have to return true in this case. We have to return boolean value true in this case, right? So the output that we got here as boolean value true, which is equivalent to the output that they have mentioned in the mentioned for the first example in the question. So our approach works absolutely correct. Our approach works absolutely correct on this case. Our approach works absolutely correct on this case, right? So let me remove this one. Our approach works absolutely correct on this case. Our approach works absolutely correct on this case, right? So here, let me tell you one thing. Yeah, let's leave it. It's fine. So we are done with the approach part. Now, as we are done with the approach part, let's move on with the complexities part, man. So what will be the time complexity here? The time complexity would be big of n because we are going with the recursion accordingly with the approach that we discussed, right? So we will be visiting each node exactly once. So overall time complexity would be big of n. Overall time complexity would be big of n. So what would be the space complexity? Space complexity would be big of h, or you can consider big of n as well. But here what happens, we'll be considering for the skewed tree, right? We are making use of the we will be or accordingly with the approach we will be making use of the recursion stack, right? So recursion depth would go up to big of n, or we can just consider height of the tree itself, because in the worst case we have to consider for the skewed tree, right, every time. So the overall space complexity would be big of h here. Big of h, the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of h respectively. Big of n and big of h respectively, right? I hope the complexities part is completely clear along with the approach. As we are completely familiar with the approach and the complexities part, now we are good to write the code. Let's start writing the code, right? So we'll be purely going with the recursion basically. First, let's make use of the helper function, man. Let's make use of the helper function. So here I'll just go with the name helper itself. So I'll just go with the, we'll be going with the pure recursion, right? So this one will be private boolean helper. So the parameters I'll just go with node. Why be here? Yeah, this is fine. I'll just go with the parameters node, min and max. So long min will be of the type long and max will be of the type long. So this is fine. Within the helper method, first thing is we will be going with the base case, nothing but if it is empty tree, then it is said to be valid. If the tree is empty, then it is said to be valid. So I can just write in this way. If node equals null, if node equals null, then we have to return true. Then we have to return true. Means this is the base case, right? If the tree is empty, then it is said to be valid. The next step is um, if node violates min or max constraint, then it's not a BST. Means here in this case, if the value is not if the left subtree's value is greater than the node's value, then it fails. Here also, if the right subtree value is smaller than the node's value, then this condition fails. If either of the condition fails, then it is not said to be a balanced binary search tree. Then it's not said to be a this one binary search tree, right? So here in this case I can write in this way: if node dot value less than or equal to min, or node dot value greater than or equal to max, then we have to return false. Then we have to return the boolean value false, right? So uh, the final step would be we have to recursively check left and right subtrace with the updated bounds. Means let me return helper of node dot left here, node dot left comma min. So this one will be node dot value. And again here this would be helper, this would be right node dot right, this would be node dot val, and this one would be max, this one would be max. This is fine. This is fine. This is it for the code basically. This is it for the code, right? So we just went with a pure recursion here, right? So we are just recursively checking left and right subtrees with a updated bound. That's it. Let me format the code once and let me hit the run button. So yeah, I didn't use this one in the main code at all, right? So just give me a second here. Yeah. So within this one, so as I've said earlier, so we have to start with, just give me a second here. Did I miss anything? No. Yeah, we have to start with the full value range. We have to start with the full value range. For that one, we have made use of the helper already, helper method. So I'll just go with the helper. As we have to start with full value range, I'll just go with root along with long dot min underscore value. And this one, let me copy the same thing, and instead of min, I'll just make this one max. So this one will be max. So this one will be long dot max underscore value. So this is fine. Let me hit the submit button, man. Let me hit the submit button. Hmm. Oh yeah, I have forgotten the semicolon. So let me give semicolon here. So let me hit the submit button. So I should have hit the run button instead of submit. So this is fine. So now you can clearly see here all the test cases are getting passed. So I have directly hit the submit button, right? So all the test cases are getting passed here. So whatever the code that we have written works good for all the test cases, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.